Hello, I'm Christian from Group 12, and today I'll be presenting along with Yuki, Caleb, and Kylan. So for question 1, we've been asked to model the interatomic distances for aluminum and iron. So let me take you over to some graphs that I made on Desmos. Alright, so here we have our Desmos graphing calculator. And here at the top left of our graphing calculator, we can see our two equations. Now, these are both the equations we've been given that represent the relationship between the total energy and interatomic distance. So as we can see here, the first one is going to be this green one, which is going to represent the relationship for aluminum. And the second one, the purple one, is going to be the relationship between the iron. So as we can see here, as this approaches infinity, or as the interatomic distance gets greater and greater, the energy total between the two aluminum or either of our material's atoms, it becomes closer and closer to zero. So as you can imagine, as two atoms get farther and farther apart from each other, the energy between them goes to zero. So now let's look at this peak, or the peak of, or the very bottom of the valley of our Nike function for this green line, which is aluminum. So at this bottom of the valley, we're gonna have our most stable energy point. Now the x here represents the interatomic distance at this most stable energy point. And for this aluminum, it's going to be 0.281 if we round to the nearest thousand. So after we go past this point of most stable energy, we get the two atoms get closer and closer. And so as they get closer and closer, the total energy between the two of them increases exponentially, and it goes up to positive infinity in the y direction, which is the total energy. Now, if we look at the purple line, which is our iron, we see a similar thing happen. Goes to zero as the interatomic distance increases. At the peak here, our most stable energy point, we have an interatomic distance of 0.283 nanometers. And then as we go past this point, it increases energy exponentially to positive infinity. And now I'll pass it on to Yuki to talk about question 2, where he'll talk about the elastic modulus and bulk modulus of both aluminum and iron.
Hi, my name is Yuki, and welcome back to Project 2, Part 2 of Material Science. In this unit, we'll be going over elastic modulus and bulk modulus. So to start things off, what is elastic modulus? Well, elastic modulus is the measurement of a material's elasticity, which is material strength to non-permanent or elastic deformation. As shown in the graph, that's an example of the elastic modulus. And the equation goes as E equals to compressive strength over axial strain equals to the symbols that represents those as shown. Young's modulus is the slope, which is equal to rise over run. Next up is an example of elastic modulus for aluminum. As elastic modulus is equal to 69 GPa, or elasticity is equal to 69 GPa, equals to 6.9 times 10 to the 10 Pa, and the formula is E, or elasticity, is equal to force divided by cross-sectional area, which is all over change in length, divided by length. And if you want to find the change in length, which is equal to force times length all over cross-sectional area multiplied by the elasticity, and plug in the numbers and you get 2.9 millimeters. Onto elastic modulus for iron, it's basically the same formula, but you plug in different numbers due to materials being different. One's aluminum and one's iron with different properties. And then for the change in length, you get 1.0 millimeters. Up next is what is bulk modulus? Bulk modulus is a measurement for materials' resistance to becoming compressed. And the equation for that is bulk modulus is equal to change in pressure over the change in volume divided by volume. And there's a diagram for that. So bulk modulus for aluminum. V is equal to, or volume is equal to 1 millimeter cubed. Change in pressure is equal to 1.0 times 10 to the 8 PA. And then the formula for this is change in volume over V equals to negative change in pressure over bulk modulus. And then the change in V over V is equal to 1.0 times 10 to the 8th. Sorry, negative 1.0 times 10 to the 8th and over 7.6 times 10 to the 10, which would give you negative 1.32 times 10 to the negative 3 meters cubed. And the bulk modulus for this is 76 GPa. And for the second, well, to change it into PA, is 7.6 times 10 to the 10. Next up is for iron. It's the same formula once again due to solving for bulk modulus. And then it's just with different numbers, with 170 GPa and with 1.7 times 10 to the 11 PA. And then solving that would give you negative 5.88 times 10 to the negative 4. And I'll pass it on from Kylan from here.
My name is Kylan McSweeney, and I'm going to be comparing the total vacancies in aluminum and steel. To calculate total vacancies, we use the equation NV equals N times the exponential times negative E over KB times T, where NV is the total number of vacancies, N is the vacancy concentration, E is the formation energy, KB is Boltzmann's constant, and T is the temperature in kelvins. To find N, the vacancy concentration, we algebraically rearrange the equation ρ, which is density, equals the number of atoms times the aluminum's mass divided by the volume times Avogadro's number. And we rearrange that to the number of atoms divided by the volume equals ρ times the Avogadro's number divided by the mass of aluminum, and that N equals the number of atoms over the volume. So plugging that back into the original equation, we get NV equals ρ times the Avogadro's number divided by the mass of aluminum times the exponential times negative E over KBT. And then we plug in our values to solve for N of V. After finding the vacancies per meter cubed of steel and aluminum, we can see that aluminum has more total vacancies than steel. Aluminum has 7.925 times 10 to the 47th total vacancies, and steel has 1.012 times 10 to the 19th vacancies. This shows that aluminum is weaker than steel because vacancies are the defects in the material structure that affect the strength of the material. So the more possible defects results in the weaker material. And another way that we can see which material is stronger is by the defect probability. To calculate defect probability, you take the number of occupied sites in the structure and divide it by the total number of sites. In terms of aluminum and steel, aluminum's structure is smaller than steel's, which would lead to the total sites in aluminum to be less than steel. This means that aluminum's defect probability will be higher than steel's, which also indicates that steel is stronger. And now I'm going to pass it on to Caleb, who's going to tell you how the total vacancies in the material per cubic meter affects the overall yield strength of that material.
In order to solve for the vacancy occurrence probability, we will use the formula NPD is equal to V total times NA times P divided by A, which is multiplied by e to the negative QV divided by KB times T power. This uses Avogadro's number, which is 6.022 times 10 to the 23rd atoms per mole. It uses the atomic mass, the volume, which in this case is 1 meter cubed, the density, the vacancy formation energy, the temperature, which in this case is Kelvin, and kBT, which is equal to 1.38 times 10 to the negative 23rd power joules per Kelvin. The atomic mass of aluminum is 26.98 grams per mole, while the atomic mass of iron is 55.85 grams per mole. After solving for the vacancy occurrence probability, we will find that aluminum has a higher vacancy occurrence probability. This means that it has more impurities, and more impurities mean a lower yield strength, which means that iron would have a higher yield strength than aluminum. In this video, we have described interatomic distance, elastic modulus and bulk modulus, vacancy formation energy, the concentration of vacancies per meters cubed, and the vacancy occurrence probability, all for aluminum and iron. We concluded that this affects the yield strength by causing iron to have a higher yield strength than that of aluminum.